Okay, parallel plates appeared in electrostatics and they gave people fits, but they're really not that scary. The basic idea is here. We're gonna take a wire and we're gonna hook it up, we're gonna take two flat, boring parallel metal plates and we're gonna hook them up to a battery. Okay. This is an oversimplified vision of what batteries do, and I'm sure chemistry people will hate me for this, but batteries essentially you can think of them as almost like stealing electrons from one side and kind of giving them to the other. So what we end up seeing is the positive end of the battery, the side connected there, is going to end up with an overall positive charge, and the negative end is going to have a lot of electrons stuffed onto it, basically until it can no longer stuff electrons on there. How does that affect things? Well, now let's look at if we were to put a tiny positive test charge in here. How is that affected? Well, positives and positives dislike each other, want to run away. So we would feel a force this direction from these positive charges. Positive charges are also attracted to negative electrons here, so we would feel a force like that from both of those. And if we add that together, we get a net force kind of pushing it down like that. What would happen if the positive charge was up here? Would that change how much force it felt? Well, if it was up here, it would feel quite a bit of repulsion. It'd be closer to the positive plate. It would not feel as much attraction because it's further away, but overall, the net force would stay the same. So anywhere you would move a charge in between these plates, you're gonna feel the exact same amount of force. That means that everywhere in between these plates, we're going to feel the same force. We are also going to feel the same electric field strength. So if you recall, force is equal to the electric field strength times whatever charge you have in there. If the force is the same everywhere for a particular charge, we know the electric field has got to be the same in there. So you get this very boring uniform electric field. And remember, field lines point away from positive and toward negative. Another way of saying that is field lines point away from high potential and they point toward low potential. One thing covered briefly in the notes is the idea of fringe effect, which is if you go out here, this kind of bubbles out a little bit. Nothing scary there. Okay, so we have this boring constant electric field, which would be the same no matter where you are. So if you were to be here, you get the same electric field strength as if you're here, as if you're here, if you're here. All right, so pretty much the key to a lot of these is actually energy. Force is helpful and you can do a lot of these problems with force, but honestly, it's way more obnoxious. So let's talk about what's going on in terms of energy. Well, we have a positive end of a battery, and positive end of the battery is associated with high potential. So over here we have high potential. The negative end of the battery, negative charges are low potential. Okay, so a lot of these things say you have a particle near one of the plates or in the middle of the plate. How fast is it going to be going? Well, the way that we're going to remember that is we're going to remember a few equations. Okay, potential energy in mechanics was written as potential energy like this. So in other words, if you had a ball up here and it was going to fall down, 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 down. And as it fell, the potential energy was going to turn into kinetic energy. So in terms of particles, it's kind of similar, except now we're going to use the symbol U. That's what potential energy is when we talk about electrostatics. What will happen is you go from a position of high potential with a little positive charge, and it's going to fall to a position of lower potential energy. So your potential will turn into kinetic energy, just like before. And that's the whole key here. So what is the potential energy? That's the real trick here. It's actually really an easy equation. potential energy in terms of electrostatics was equal to V times Q. In other words, the change in the potential times the charge of whatever's moving through that potential. So let's start with the easiest situation. I'm going to give you a little example here. Let's say we hooked this up to a 9-volt battery. We had 2 parallel plates hooked up to a 9-volt battery. And we were to put we'll put a little positive charge over here, okay? Do positives go from high potential or to low potential, or low potential to high potential? So they will go towards low potential. So they're going to go from high to low. So let's say we were to cut a little hole in here. Oops. We're going to cut a little hole in here. So this particle is going to go down and go zipping out that hole. Okay. So what we're going to do is get a 9-volt here. And let's say that this was a little proton. We know protons don't move, but we'll go with it. Okay. So the positive charge of positive 1.6 times 10 to the negative 19th coulombs. Okay, so if we wanted to know the potential energy up here, we'd say, all right, as it moves from here down to here, it's going to go from 9 volts to 0 volts. So it's going to go through a change of 9 volts. Okay, so that's our V. We know our Q, and we're going to do math, and we're going to get, so math, and we get the potential energy is 1.44 times 10 to the negative 18th joules. Okay, so that's how much potential is going to turn into kinetic as it goes from this position to this position. So that is the kinetic energy that we are going to have. Okay. So how does this energy help us? Well, if you know the kinetic energy, you can use K is equal to mv squared divided by 2. You know the kinetic energy, and we could look up the mass in our equation sheet for the mass of a proton, because I said it was a proton, and we can solve for the velocity. So I just looked that up, and the mass of a proton in kilograms, 1.67 times 10 to the negative 27th. So now we have the kinetic energy, we have the mass, we found the potential as it moves between the plates, so now we can go after our velocity, and we're going to do that by sticking it in here. So they often like to ask what the acceleration is too. So what would the acceleration be? Well, this would be the velocity when it's about to hit this plate or go through the hole on this plate. So that's our final velocity in here. Our initial velocity would be, what is it? 0, yeah, because it starts from rest. We're looking for the acceleration, question mark, and you're like, well, we don't have anything. Well, I didn't really give it to you. They often give you the distance between these plates, very, very, very often. So let's say these plates were separated by 0.1 meters. Actually, it's pretty big. Let's make it 0.01. So how do we do that? Well, we have our distance now is 0.01, and we don't know and we don't care about time, so we have to choose the equation that does not have time in it. This is reaching way back to last year when we basically beat these equations into, and that is, sorry, I'm on a spaceship apparently. So, jeez. So that would be VF squared is equal to VI squared plus 2AD. Memory? Okay, good. So we can plug that in. 4.15 times 10 to the 4th equals 0 plus 2A 0.01. And then math.